Welcome to ISE 331, Stochastic Models. I'm your instructor, John Gunnar Carlson, and in today's lecture, we're just going to talk about what stochastic models are. We're going to do some examples, and we're going to talk about the history of stochastic models. So what does the word stochastic mean? You probably don't know this word. It's a fancy SAT word that just means random. We say things are random as to distinguish them from being deterministic, which is what you'd study in ISE 330, which means not random. A stochastic model is just a mathematical formulation, which means it's an equation or an algorithm or a theorem that is used to model or solve a real-life problem where the inputs are known with uncertainty. That's the stochastic bit. It means you don't know what all of the inputs are going to be. There are probabilities that are present. You say there's a 60% chance of one thing happen and a 40% chance of another. This comes up all the time in weather forecasting. It comes up all the time in gambling by definition. It comes up in elections. It comes up in most quality control. What are the purposes of stochastic models? There are four I can think of. The one would be to explain a phenomenon. You could say, why is it that the grades when you take a final exam tend to look like a bell curve? Where does that come from? There's a mathematical model for that called the central limit theorem that expresses that. You might want to make a prediction. You'd want to know who's going to win the election tomorrow. We use confidence intervals for that, together with hypothesis testing. You might want to use decision support. You might want to know the answer to a managerial problem you're trying to solve. How many checkout lanes should I put in my grocery store? The amount of demand I'm going to have in my store each day is random. Am I going to have 14 customers, 20, 0? I don't know that, but I want to have the right number of queues or checkout lanes in my store to make sure people leave quickly enough to make a lot of money for me. There's a whole mathematical field of this called queuing theory, which you're going to learn in the very tail end of this course. Finally, communication. Right? Sometimes a mathematical model is useful just because you're able to articulate something to a client or to a supervisor. The Pareto principle says that 80% of your sales come from 20% of your clients, or more generally, 80% of your effects come from 20% of your causes, the 80-20 rule. This isn't just a nice statement, it actually has some beautiful mathematical reasoning behind it due to Vilfredo Pareto around the turn of the century. Let's look at some history of stochastic models. And to do this, we have to go back to the beginning of where probability was even formulated by mathematicians. And that, I think, starts in the 1500s. Girolamo Cardano was a Milanese physician and mathematician who was a game addict. He described the practical and theoretical aspects of gambling in a book on the games of chance, which he called Liber de Ludo Alii. I probably butchered that. He defined chance as being the ratio between the number of times you win a game divided by the total number of times you play the game. Okay, this is a predecessor to what we call expectation, which you've probably seen in a probability course. Cardano's book remained unpublished until 1663, by which point it was rendered obsolete by works of people like Pascal, Fermat, and Huygens, who formalized this notion of expectation of a random variable. There's a quotation here that talks about just how addicted to games Cardano was. In 1713, Jacob Bernoulli I proved the weak law of large numbers, which you probably don't remember but probably have seen before in his book Ars Conjectandi. We're going to revisit all of this stuff, so you don't have any obligation to have it ready on hand at the moment. This showed you how to measure the closeness in terms of probabilities between the average values of a random sample and the actual values that you see. Okay, if I flip a coin 1,000 times, I know that I'm going to see heads about 500 times, provided that that coin is fair. But what does about mean? All right, if I see 550 heads, is that unreasonable? Well, probably not. That seems reasonable enough. But if I see heads 900 times, we can all agree that that would be profoundly unlikely. And what Jacob Bernoulli did was express this statement precisely in formulating the weak law of large numbers. At the same time, his nephew, Nicholas Bernoulli II, posed 5 problems in probability, one of which is a famous one called the St. Petersburg paradox, and that describes a game whose expected value is infinite. It works like this. Let's say I have a fair coin, like the one I'm holding here. This is an Eisenhower dollar. And we're going to play a game like this. I'm going to flip the coin, or actually you're going to flip the coin. And you're going to keep flipping it until heads shows up for the first time, at which point the game is over. And I'm going to pay you depending on how many flips it took until you saw heads for the first time. So we'll say that if you see heads on the very first flip, you get $1. If you see heads on your second flip, then you get $2. If you see heads on your third flip, you get $4. And on heads on the fourth flip, you would get $8, and so on and so forth. So the amount that you win doubles with each time that you flip the coin and you don't see heads. So the question that Nicholas Bernoulli asked was, how much should I be willing to pay this game? And if I were to take a survey right now, before I proceed with the analysis, you might think to yourself how much you'd actually be willing to pay to play this game. Let's figure out how much this game is worth us to play. So what are the options here? Let's write down what could happen. Maybe I get heads, or you get heads. You're the one playing the game. If you see heads on the very first flip, then you would earn $1. And what is the probability of that happening? It's 1/2, because you'd either get heads or tails on your very first flip. What is the probability that I see heads on my second flip for the first time? That means I'd have to get tails on the first flip and then heads on the second. At that point, I would get $2. And what's the probability of that happening? Well, that's just the probability of seeing tails and then heads, which is 1/2 times 1/2, which is 1/4. What's the probability that I see heads for the first time on the third flip? That's the probability of me seeing tails and then heads. And at that point, I would get $4. And what is the probability of that happening? Well, I'd have to see tails and then heads. So 1/2 times 1/2 times 1/2, which is 1/8. One more example. I think you see the pattern. I'm going to get $8 if heads occurs on my fourth flip, which would be tails, 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 heads. What's the probability of that happening? Of course, it's 1/16, because I'd see tails 3 times, and 1/2 probability of each of those, followed by heads. So you'd see things would proceed in the manner that I've written down here. So how much am I going to win if I play this game? How much on the average do I expect to win? Well, let's take these, let's write these numbers out here and compute what is the expected value, if you remember that term from probability. Well, what'll I do? I'll take these probabilities here, and I'll bring them down like that. I'll say, well, there's a 1/2 probability of making $1. And then there's a 1/4 probability of making $2. There's a 1/8 probability of making $4. And there's a 1/16 probability of making $8. And so on and so forth. There's a 1/32nd probability of making $16, and so on and so forth. What do I get when I total these numbers up here? Well, I've got 1/2 times 1, which is 1/2, plus 1/4 times 2, which is 1/2, plus 1/8 times 4, which is 1/2, plus 1/16 times 8, plus 1/2. So what am I doing here? I'm adding 1/2 together infinitely many times, because this pattern is going to repeat as I make the number of flips get higher and higher. So what does this sum converge to? It doesn't converge to anything. It's infinity, because I'm adding 1/2 to itself infinitely many times. And so therefore, this game has an expected value that is infinite. The value of this game is infinity. But that's contrary to common sense, because anyone who looks at this game is probably not willing to spend more than $3 or $4, if we're being generous, to take a crack at it. So that's one of Nicholas Bernoulli's 5 probabilistic games. In 1733, Abraham de Moivre stated a form of the central limit theorem by establishing the existence of what is called the normal distribution, or the Gaussian distribution, or the bell curve, which you can see over here. You've probably seen these kinds of curves before. We call this a Gaussian distribution now, but it was actually rediscovered by Gauss in 1812. The context in which de Moivre discovered this distribution is actually he was trying to approximate the binomial distribution, which you might have remember from a probability course. But again, I'm not going to assume you know that. We're going to review all this stuff. 1763, the English Reverend Thomas Bayes wanted to figure out mathematically how to infer causes from effects. He said, how can I learn the probability of a future event occurring if I only know historical information? He was talking about things in the context of causality. He said, if I know that A often causes B, and then we observe that B has occurred, how likely is it that A has also occurred? I've got written here the Bayes rule. This rule has been the bane of many a probability student. It involves what is called conditional probability, which a lot of students don't like. Just very quickly here, let's look at what's going on here. This expression here, the probability of A given me, that vertical line between the A and the B is pronounced the given. The probability of A given B. What this thing here on the left means is the probability of A being true if I know that B is also true. Okay, because B might be something that influences A, right? If B is raining outside, A would be maybe the event of me getting stuck in traffic, which is probably a lot higher if there's rain. Anyway, the Bayes rule says I can talk about the probability of A given B as a function of the probability of B given A, provided you multiply out by the ratio of these other two probabilities as we're doing there. We're going to revisit Bayes rule. You've probably seen it before, but you've probably forgotten it, so we're going to go over that again in a lot of detail. Maybe you've seen pictures that look like this. This is called Brownian motion. This was first discovered by Louis Bachelier, who was a student of Poincaré, who developed a framework for modeling the movement of stocks, and we now call this Brownian motion. This actually is something very interesting. This is what is called a stochastic differential equation. You might have seen differential equations before. Maybe the most common context is one where you talk about small increments of time moving along and some function that is varying with respect to that. When we talk about a stochastic differential equation, we now talk about something called an infinitesimally small amount of randomness, which I've written here with the delta WT. It's a very complex abstract concept, not something we're going to talk about in this course, but a very interesting one. 1907, Markov processes and chains. That's going to be probably the most important focus of this course, is for you to understand what a Markov chain is. So in 1907, Andrei Andreevich Markov developed the concept of what we call Markov processes from his studies on experiments that were connected in a chain, and you'll be very comfortable with what I mean by that a few weeks into this course. A Markov process is just a stochastic process where if we know the current state of the process, the future depends only on that state and not anything that's in the past. So the Markov property is something I've written here. It sounds like a great motivational poster. It says the future is independent of the past given the present. In other words, it doesn't matter how you got to where you are. Everything in the future only depends on where you are at that moment. This is a natural kind of premise that applies to a lot of situations, and it's very useful. It's mathematically really tractable, and it's fun. So there's a lot of use to be gained out of that. I've written out what it means mathematically in terms of conditional probabilities here with this big messy thing, and by the end of the course, you'll be very familiar with what I've written there. Right now, that probably looks like a lot of gibberish, but you'll be familiar with it by the time we finish. 1909 was when we saw people laying the foundations of queuing theory, which is the last unit we're going to talk about in this course. Erlang used probability theory to model telephone traffic, showing that incoming calls, the rate at which they were coming in, would be approximated well by the Poisson distribution, which you might remember. This led to the foundations of modern queuing theory, which is simply the mathematical study of people getting in lines and waiting for things. This process was improved by Edward Molina, who wrote a book in 1928 that was used for decades, although it's fallen out of popularity as of late. I've got a queuing diagram sketched over here. You have inputs, You have a queuing process, you have a server process, and then you have things leaving that queue. I myself took 2 semesters of queuing theory in grad school for mostly for the pleasure of being able to complain more precisely about toll booths and bank lines in grocery stores and things like that. A lot of people really hate probability. It's because humans aren't very good at it in general. Our brains aren't really wired to accept mathematical formulations of randomness and to believe that that's generally how the world works. I'm going to go through a number of examples here, which I encourage you to think about just to see how your brain addresses this kind of uncertainty. The first one is called the 3-card swindle. In the box here to the right, I'm talking about cards having spades and diamonds on them. But visually, I find it more helpful to look at colors. So I'm going to do things using red and blue cards, as you see here. The 3-card swindle, as it was called by Martin Gardner, involves the following process. I have 3 cards that you see here. One of those cards is blue on both sides. One of these cards is red on both sides. And the third card is red on one side and blue on the other. So I've got 3 cards like that. I mix them up into a box or a hat, and I take one out, and I look at one side of it. Okay, I look at one side here, and I see that this side is red. So I now ask myself, I know that one side is red, and therefore, given that one side is red, I know I'm not holding that card that is blue on both sides. So I can throw that out of consideration. So now I know that I'm holding one of 2 cards. Either I'm holding the card that is red on one side and blue on the other, or I'm holding the card that's red on both sides. Let's ask what the probability is of either of these events. It's intuitive to say that, well, I started with 3 cards. I ruled out one of them. So therefore, I've got 2 choices left. And so there's a 50-50 chance that I'm holding either the red and blue card or the red and red card. That's the tempting way to look at things. It's also unfortunately wrong. In fact, the probability that the other side of this card is blue is not 1/2. It's actually 1/3. And I happen to be holding the right one by coincidence. That wasn't some sort of dramatic effect. That surprises people because it's tempting to say that, well, if I've ruled out the one card, then the other 2 are equally likely. That's not the case. And we'll pick that one apart and unpack it later in the course, and you'll see where that comes from. The shooting room paradox is another great example of counterintuitiveness in probability. So let's say you have a room, and you enter that room. You're going to play a game that works like this. You enter the room and roll a pair of dice. 2 things are going to happen. If the dice show double 6s, like that, then the game is over. The person who entered the room gets a swift kick in the shins, as I wrote, and the game is finished, and they go and limp home in pain. If the result on those dice is anything other than 2 6s, that person walks out of the room, receiving no kick in the shins. They're as happy as can be, and now 10 people enter the room instead. And those 10 people are going to participate in the same kind of game. So 10 people are now going to walk back in. And once again, we've got 10 people in the room, and we're going to roll the dice. So if the dice show double 6s, all 10 of these people get a kick in the shins, the game is over, and what's done is done. If the result on those dice is not 2 6s, then those 10 people leave, and they get replaced by 100 people who now enter the room. Once again, you roll the dice. If you get 2 6s, they all get a swift kick in the shins. If the result is anything other than that, they all leave, and they are replaced with, you guessed it, 1,000 people who entered the room. Okay, so this game keeps proceeding that way until double 6s is rolled, at which point the people who are in that room, which is probably a very large number at that point, gets a swift kick in the shins, and the game is over. It's called the shooting room paradox because it originally involved killing all the people in the room, but I thought that was a little too graphic. So why is this counterintuitive? What is weird about it? Think about this game from 2 perspectives. Let's suppose you learned that you are going to be called to play this game. Say, oh, you're up next to be part of this swift kick in the shins walking into the room. Are you going to be worried about this? Probably not, because you're going to say, I don't think double sixes is very likely. I'm going to walk into the room. Someone's going to roll these dice. It's probably not going to be double sixes. I'll probably walk away and I'll be fine. Fine. That's all well and good. However, let's suppose your mother learns that you played this game. Your mother is going to be terrified. Why is she going to be terrified? Because more than 90% of the people who play this game end up getting a kick in the shins. Right? Let's imagine the following situation here. So why do I say 90%? Where does that come from? Well, let's say, what does the sequence look like? Let's say you have one person walk in the room and they don't roll double sixes. And so then there's 10 people walking in the room. We still don't roll double sixes, let's say. And then 100 people who walk in the room. Again, let's say no double sixes. And then for want of anything else, we'll say that on the time that the third round of the game, sorry, that's the fourth round of the game, with 1,000 people, you then have double sixes, and all these 1,000 people get a swift kick in the shins. Well, how many people got a swift kick in the shins? 1,000 of them did, divided by how many total players did you have? Add these numbers up. All in all, it's 1,111, which is greater than 90%. So someone else hears about you playing this game, they'd be very concerned. If you learn that you have to play this game, you're probably not very concerned. A little counterintuitive, so I encourage you to think about that to yourself and try and reason through why that is the way it is. The Carter-Leslie doomsday argument is referred to by some philosophers as a mathematical proof that the world is going to end soon, or a probabilistic argument of that sort. And it looks like this. We have two big urns in front of us. I'm going to use these two boxes here. And I know that one of these boxes has 10 balls in it, and the other one has a million. I don't know which one is which. Okay, I don't know which one of these has a million. I don't know which one of these has 10. I select one of the boxes at random, and I reach in, and I grab a ball. And I look at the number on that ball. I see the number on that ball says 7. What would I conclude? I would say, well, it's very, very likely that there are 10 balls in this box, and therefore a million balls in the other one. I don't think anything I've said so far is controversial, but let's now ask about the implications of this. Let's visit that doomsday argument again, but we'll now think about things not in terms of balls lying in urns, but in terms of the future of the human race. Let's say that we have two boxes as before, and each of those boxes represents a possible future for the human race, one of which where the world ends very soon, and one where the world ends much later, and we multiply throughout the universe for millennia to come. So let's say that there's two possible outcomes. There's the one where the world's about to end, and the one where we have a long ways to go. So you pull out a ball, and you look at the number on it. That's like you being born. You're born, and the number, an order of your birth is the number attached to that. For example, you are roughly the 60 billionth person to be born. So if I pull out a ball and I see that the number is 60 billion, well, it's not very likely that the number of balls in that urn is in the quadrillions. It's unlikely I would have sampled one that was that small. And so therefore, the reasoning is a rank of 60 billion or so, meaning being the 60 billionth or so person to be born, is much more likely if only, give or take, 100 billion people will ever have lived than if there are going to be many trillions or quadrillions of people multiplying throughout the universe. So therefore, an impending doomsday is highly probable. That's the Carter-Leslie doomsday argument. I encourage you to think about it and reason about it to yourself, and see what about it makes sense to you and what doesn't.